Welcome back to AI.Code.Cast. Today, we're going to be doing a deep dive into this pretty interesting problem.
Okay.
It's all about finding, like, the shortest bus route,
Yeah.
which sounds kind of simple,
Yeah.
right? But
It does sound simple, but
it can get really complex.
yeah, so like imagine you have like all these different bus routes in a city.
Mm-hmm.
Like you've got a list of them.
Right.
And you need to figure out like how to get from point A to point B with the least amount of transfers.
Exactly. Yeah.
And it's like we do this all the time, right? Like when
Okay.
we're using Google Maps or whatever.
All the time.
But like how do you code that?
Well, the most basic way to do it is you just try every single combination of routes.
Mm-hmm. Okay, so you just like
Brute force it.
brute force it.
Until you find the shortest one.
Okay, and that doesn't sound too bad.
But imagine, like, if you live in a small town, that might work.
Right.
But if you live in, like, New York or something with hundreds and hundreds of routes.
It would take forever. It would take forever. Your computer would probably crash.
Yeah, you'd be waiting and waiting.
Yeah.
Okay, so that doesn't sound very efficient.
Not at all.
So how do we make it smarter?
So that's where this algorithm called breadth first search comes in.
Okay.
BFS.
BFS. Have you heard of that one?
I have, but I always get a little like, oh no, when I hear algorithms.
Okay.
So like maybe we could just like quickly recap what that is.
Yeah, so breadth first search is basically an algorithm that systematically explores a network or a graph.
Okay.
So imagine like a tree with a bunch of branches spreading out.
Mm-hmm.
You start at the root of the tree, or your starting bus stop in this case.
Right.
And you explore all the neighboring nodes or the stops that are directly connected by one bus ride.
Okay, so it's like checking all the stops you can get to with just one bus.
Exactly.
Got it.
And then for each of those neighboring stops, you do the same thing.
Okay.
You explore their neighbors and so on.
So it's like kind of like ripples in a pond. It's like going outward like that.
Exactly.
So it just keeps going layer by layer until it finds the destination node or your target bus stop.
Okay, so it's not just randomly checking roads. It's actually going through like in a systematic way.
Yes, exactly.
And because it's doing that systematically,
yeah,
it's guaranteed to find like the shortest path.
Yes, in terms of the number of transfers.
Okay, that makes a lot of sense.
Yeah.
So, okay, so we kind of got what BFS is, but how do we actually use it for this bus problem?
So there are two main approaches to applying BFS to this problem, and they both involve a clever little twist to how we think about the problem.
Okay.
One uses what we call a stop route map,
Okay.
and the other treats the bus routes themselves as nodes in a graph.
Okay. Those sound pretty interesting.
Yeah.
Let's start with that stop route map thing.
Sure.
What is a stop route map?
So imagine you have this giant map of the city, but instead of showing you streets and buildings,
Okay.
it shows you all the bus stops. And for each stop,
Okay.
you have a list of all the bus routes that pass through it.
Oh, so it's like a cheat sheet for each stop.
Yeah.
So you're like, okay, I'm at this stop, and then these are all the buses I can take from here.
Exactly.
Okay, so how does that map actually help us?
So instead of checking every single route combination, we can use this map to jump directly to the routes that are actually relevant.
So we're not wasting time with routes that don't even go near where we want to be.
Exactly.
Okay, that makes sense.
Yeah, so we start at our source stop. We look up all the routes that pass through it on our map, and those routes become like our first layer of exploration.
Oh, so it's like we're saying, okay, from here, let's see where I can go with just one bus ride.
Exactly.
Got it.
And for each of those routes, we check all the stops it covers. If our destination is on one of those routes, great, we found the shortest path.
And like we said before, the number of routes we've checked is like the minimum number of transfers, because each route is like a potential transfer, right?
You got it.
Okay.
But what if our destination isn't on any of those initial routes?
So we got to keep searching, right?
Yeah.
But instead of just like trying any random route, we can use our map again.
Yes, exactly.
Okay, so how do we do that?
So we look at all the stops that we reached in that first layer
Okay.
and use our map to see what other routes pass through those stops.
Okay.
And those become our second layer of exploration.
So it's like, okay, if I take one bus ride, these are all the places I can get to. And then from those places, what other buses can I take?
Exactly.
Right.
And we just keep doing that layer by layer, using our map as a guide until we finally find our destination.
Okay. I'm starting to see how this is way smarter than just brute forcing every route.
Yes.
It's like we're strategically hopping between routes,
Yeah.
always getting closer and closer to the target.
Exactly. And because we're only looking at relevant routes, this method is very efficient.
Oh, so that's why it's faster.
Yes.
Okay. This is making a lot of sense.
Good.
So using this stop route map with BFS is kind of like having like a super powerful navigation system.
Absolutely, yeah.
Okay, this is fascinating. Now, I'm really curious about that second approach you mentioned,
Okay.
the one where we think of the routes themselves as nodes.
Yeah.
How does that even work?
Yeah.
Well-
So let's dive into that. All right. So instead of focusing on each individual bus stop,
Okay.
we're going to zoom out and look at the routes themselves.
Okay, so instead of like a map with all these like tiny dots for all the stops,
Yeah,
we're thinking more about the lines that connect them.
exactly.
Good.
And the connections between those routes, those happen when two routes share a common stop.
Oh, okay, so like if route A and route B both stop at Central Station,
Mm-hmm.
then in our graph, like they're connected.
Exactly. They're connected.
Okay, I like that.
Yeah. So instead of having a huge graph with every single stop,
Right.
we now have a much smaller, simplified graph of these interconnected routes.
Okay, so we've kind of like condensed the problem down.
Yeah, exactly.
But like, how does BFS actually work in this new graph?
Right.
We're not like hopping between stops anymore. We're hopping between routes.
Exactly.
Yeah.
So we start by looking at all the routes that contain our starting bus stop.
Okay.
Those become our initial nodes.
So it's like saying, okay, I'm at this stop. What buses can I get on right now?
Exactly.
And then for each of those routes,
Mm-hmm.
we check if our destination is like on that route.
Yeah.
If it is, boom, we found a path.
We found a path, and the number of routes we've explored
Right.
is the number of transfers.
Just like before.
Exactly.
Okay.
But what if none of those initial routes actually take us to our destination?
Well, then we need to like hop to a different route.
Yeah.
But we don't want to just pick any random route.
Right. We want to pick one that will get us closer to our destination.
So how do we know which route to pick?
So that's where this route as nodes graph is really useful.
Okay.
So we look at the routes that we've already explored
Okay.
and see which other routes are connected to them, meaning they share a common stop.
Oh, so it's like saying, okay, I took this route. It dropped me off at these stops.
Mm-hmm.
Now, from these stops, what other routes can I take?
Exactly.
Okay.
And we just keep doing that, hopping between these connected routes, exploring outwards until we finally hit a route that contains our destination stop.
Got it. So it's still BFS. It's still like that ripple effect.
Exactly.
But we've like totally changed our perspective.
Yeah.
It's not about individual stops anymore. It's about the routes.
Yeah, it's a higher level view.
Yeah.
And you know what's really cool about this approach?
What?
This approach really shines when you have a lot of overlap between your bus routes.
Oh, why is that?
So think about it. More overlap means more connections in our route as nodes graph,
Okay.
right? And more connections means fewer nodes for us to actually explore.
So it makes the search faster.
Exactly.
Oh, it's like taking shortcuts.
Yeah, like shortcuts.
The more interconnected the routes, the faster we can find our way around.
Exactly.
This is awesome.
Yeah, it's a cool way to think about it.
So we've got the stop route map, which is like a detailed guide for each stop.
Mm-hmm.
And then we've got this route as nodes approach, which is more about seeing like the big picture.
The big picture connections.
Yeah, and they both use BFS.
Exactly. It's the same underlying principle,
That's really cool.
but with a different twist.
Yeah, so it's like having a toolbox full of these different techniques.
Yeah.
And it's like, okay, which one do we use for this particular problem?
Exactly.
So now that we've talked about these two approaches, maybe we could talk about how we would actually like implement them like in code.
Yeah, definitely.
But like, I don't want to get too technical.
Yeah.
So maybe we could just talk about the general idea with like pseudocode.
Yeah, pseudocode is a good way to understand the logic without getting bogged down in the syntax.
Right.
So let's start with the stop route map approach.
Okay.
So how would we represent that map in code?
Hmm.
A dictionary or a hash map would be a good choice for that.
Oh, yeah. Okay, so each key in the dictionary would be a bus stop.
Exactly.
And then the value for that key would be all the routes that pass through that stop.
Exactly. It's like a lookup table.
Yeah,
For this stop here are all the buses you can catch.
got it.
Now for the BFS part, we need a way to keep track of the stops that we've already visited.
Right, because
Yeah.
we don't want to keep going back to the same stop over and over.
Exactly.
Waste of time.
So a set would be a good data structure for that.
Okay, a set.
Yeah. And, of course, we need our queue to manage our exploration.
Our queue. So that's our like to-do list.
Yeah,
It just
exactly.
stops.
So we start by adding our source stop to the queue,
Right.
and then we enter a loop
Okay.
that continues as long as there are still stops in our queue.
Okay.
And in each iteration of the loop, we dequeue a stop.
Okay.
use our map to find all the routes that pass through it.
Mm-hmm.
And then we basically simulate taking each of those routes, checking every stop along the way to see if it's our destination.
Okay.
And for each new stop, we check if we've already visited it.
Right.
If not, we add it to the queue.
So it's that ripple effect again.
Exactly.
We're going outward.
Expanding our search.
Using the map.
Yeah, the map is our guide.
This is cool.
Yeah, and the loop just keeps going until either we find our destination or the queue is empty, meaning we've explored all the possible paths.
That makes sense.
Correct.
Okay, so how about the route as nodes approach?
Yeah.
Is the pseudocode, similar?
It follows the same basic BFS structure,
Okay.
but the data structures are a bit different.
Okay.
So instead of that stop route map, we need a way to represent the connections between routes.
How do we do that?
So an adjacency list is a common way to represent a graph like this.
Okay, yeah. An adjacency list, so it's like each route has a list of its friends,
Exactly.
the routes that it's connected to.
Yeah. So if Route A and Route B both stop at Central Station,
Right.
they'll be on each other's lists.
Okay, so we're capturing all those relationships.
Yeah, based on those shared stops.
Okay, and then the rest of the BFS is pretty similar, right?
Yeah, you got it.
We use a queue and a set to keep track of the routes we visited.
It's the same core logic,
Okay.
just applied to a different perspective.
This is really cool.
Yeah, it's fun to see how these things work.
So we've got these two different ways to solve the shortest bus route problem using BFS.
Yeah.
And we even talked about how to implement them in code.
Yeah, and you know what's even more exciting?
What?
These algorithms aren't just theoretical things. They're actually used in the real world.
Oh, I bet.
Yeah, they have a lot of applications.
I'm already thinking about Google Maps and all that stuff.
Let's talk about some of those real world applications in the next part.
Yeah, okay. Okay, so we're back. And we spent the last two parts really getting into the nuts and bolts of these BFS algorithms for finding the shortest bus route.
Yeah, we did a lot of brainstorming.
Yeah. But these aren't just ideas, right? They're actually used in the real world.
Oh, absolutely. These algorithms are everywhere.
So tell me, where do we see them in action?
Well, anytime you need to find the most efficient path through a network, these algorithms can be really helpful.
Okay.
Think about transportation and logistics, for example.
Okay, yeah, so those delivery apps that somehow figure out the best route, even with traffic and all the stops.
Yeah, how does that even work? It's probably using something like BFS.
Right.
Companies like Amazon or FedEx use these kinds of algorithms to optimize their delivery routes all the time.
And that saves them time and money and fuel.
All of the above.
Yeah, which is good for everyone.
Yeah, and it's not just about saving money.
Right.
It can also help reduce their environmental impact, too.
Yeah, for sure. Less fuel, less emissions.
Exactly.
Okay, so it's good for the planet and good for business.
Exactly.
All right, so that's delivery. But what about public transportation?
Yeah, definitely. So imagine a bus or train app that uses these algorithms
Okay.
to suggest the quickest routes, even during rush hour.
Oh, man, that would be a lifesaver.
It would make commuting so much easier.
Especially if it could adapt to real-time traffic and delays.
Yeah, imagine that.
It'd be like having a personal travel assistant.
It really would.
Okay, so we've got delivery, we've got public transport. What else?
Well, these applications extend even beyond transportation.
Okay.
Think about network routing,
Network routing.
how data travels across the internet.
Oh, so all the stuff I look at online
Yes.
is using BFS.
In a way, yeah.
Wow, okay, explain that one to me.
So these algorithms can help find the most efficient path for data packets
Okay.
to travel across the internet.
Mhm.
And that helps optimize your internet speed.
So when I'm streaming a video and it doesn't buffer,
Exactly.
that's because of BFS.
It could be part of the reason, yeah.
Okay.
And it's not just about speed.
Right.
These algorithms also help ensure reliability.
So my data actually gets to where it needs to go.
Exactly, even if there are problems along the way.
Oh, so it's like a backup plan for the internet.
Yeah, you could think of it that way.
Okay, so it's
Yeah.
speed and reliability.
Yeah,
So that's how we get all those cat videos.
among other things.
Okay, so we talked about transportation, we talked about the internet.
Mhm.
What else? What other amazing things can BFS do?
Let's step into the world of social networks.
Social networks. Okay, so Instagram and Twitter and all that.
Exactly.
Okay, so how does BFS fit in there?
Imagine using these algorithms to analyze the connections between users.
Okay.
You could identify influencers or track trends or even try to predict what content is going to go viral.
So it's like having a secret map of social media.
Yeah, you could think of it that way.
Wow. Okay, so what else can we do with it?
So it goes beyond just analyzing the network.
Yeah.
These algorithms can actually be used to personalize your content feed,
Okay.
recommend connections,
Mm.
or even help form new online communities.
Oh, that's cool. So it's like shaping the way we interact online.
Exactly.
Wow. So BFS is everywhere. It's in our phones. It's on our computers. It's like all around us.
Yeah, it's pretty amazing how these algorithms have become such an integral part of our lives.
Yeah. And this deep dive has really made me appreciate how powerful they can be.
It's not just about code.
Right.
It's about solving real-world problems.
Right. And making things work better.
Exactly, and who knows what other applications we'll discover in the future.
Yeah. I'm sure there's a lot more to come.
Yeah, as technology keeps evolving, we'll find even more creative ways to use these algorithms.
Well, I'm excited to see what the future holds.
Me too.
And thanks for joining us on this AI.Code.Cast adventure.
Yeah, thanks for having me.
We'll be back with more deep dives into the amazing world of algorithms.
Looking forward to it.
But until then, keep exploring, keep coding, and keep those cat videos coming.